So far we've got the nth term test and telescoping series test. It's not really a test, but telescoping series and geometric series as a way to decide if something converges, and if so, perhaps what the sum is. That's not nearly enough. We need a lot more tests, and it's going to continue with the integral test. Now, the integral test basically says if this summation is convergent, happens exactly when this integral is convergent. So why is that true? Well, if you take a look at this example, suppose we're summing up what Euler did, the reciprocals of the squares, then you can kind of think of this as being an area. And that area is really exactly what we calculate when we're summing up the reciprocals of the squares. Now, these areas are pretty closely approximated by the associated integral. Now, you can use a right-hand method or a left-hand method to find your points of approximation, etc. But the bottom line is that these areas here in the squares and the rectangles are pretty close to what's happening with the area for the curve. So whenever this series, whenever the integral is finite, that is, converges, so does the series. So if you want to investigate one, it's good enough to look at the other. And so that's going to be our integral test right here. So let's apply that to a lot of examples. And we're going to restart things here with example A. So that'd be the sum from n equals 1 to infinity of n over n squared plus 1. So we want to investigate whether this converges or diverges. Now, in order to use the integral test, there's three things that need to be true. It needs to be decreasing, it needs to be continuous, and it needs to be positive. Well, plugging in numbers in here is not going to give us anything except positive numbers for our summation 1 to infinity, so we're okay there. The function n over n squared plus 1 is continuous. How would you show something is decreasing? What could you do? Show that a function is decreasing. Well, you can look at its derivative. What has to be true of the derivative to show that something is decreasing?
Less than 0.
Yeah, it has to be less than 0. And that's going to be true as well for this particular example. So in order to find if this is going to converge or not, we can look at the integral from, say, 1 to infinity, matching this of, we'll do x's here, x over x squared plus 1 dx. Uh-oh, there's something wrong with this. Does anyone remember or recognize what's wrong here? What would I be tempted to take off a point for?
You have to have it be the limit as b approaches infinity.
Perfect. This is an improper integral, so we're going to rewrite it like this. So, okay. And this one's not too bad of a problem. What you should see is that the degree in the numerator is 1 less than the degree in the denominator. And that's suggestive of a u substitution. You could let u equal x squared plus 1. du would be 2x dx. So 1/2 du equals x dx, which is nice because 1/2 du, or the x dx, is exactly what I have in the integral. So I can make my u substitution. I'll also be really formal and change my limits of integration. So let's see. U of 1 would be 2. u of b would be b squared plus 1. At least I don't have to worry about my limits anymore. I'm not going to go back to x at all. I'm just going to keep it here. So that's going to be the limit as b approaches infinity of the integral from 2 to b squared plus 1 of, well, that's 1/2 du over u. The 1/2 can come out in front of the integral. In fact, it can come all the way out in front here, since it's independent of b. Limit as b approaches infinity of the integral of 2 to b squared plus 1 of 1 over u du. Well, what's going to happen here? What's the antiderivative of 1 over u?
ln of u.
ln of u, thank you. ln of u between 2 and b squared plus 1. Now the 1/2 is going to multiply this part right here. So let me just kind of leave it out in front. 1/2 times the limit as b approaches infinity of the ln of b squared plus 1 minus the ln of 2. As b squared gets really, really large, what's going to happen to this term?
It goes to infinity.
Yeah, it goes to infinity. So the integral diverges, and that tells me that the summation must diverge as well. So therefore, the sum diverges by the integral test. The integral diverges, so does the summation. So it diverged. Okay. How are we looking with that one? I think the big thing in that one was to just work our way through the u substitution, but it wasn't too bad of a u substitution. Any follow-up on this one? All right, let's do some more. There we go. All right, so example B, summation from n equals 1 to infinity of n to the 7th e to the negative n to the 8th power. Kind of bizarre looking one. You could rewrite this by getting rid of the negative exponent. That negative is no longer there. It might look like it's there, but it's really just an artifact of my camera. We could kind of, like when you, hopefully you don't look at the sun, but if you did look at it for a few minutes, you get kind of like a burn-in. That image would stay there. But there we go. It's gone. Now, let's take a look at a few things. First of all, for positive values of n, this is going to be positive. And let's see, it's continuous. That's polynomial, that's continuous. E to a continuous function is also continuous. And it's going to be decreasing. So all of that means is that I can apply the integral test. So we're going to do that to this term right here. Let's take a look at the limit as b approaches infinity of the integral of 1 to b. And you could use whatever variable here you want. We could do it with n's, we could do it with x's. I think a lot of people are probably in their comfort zone if I use an x. Like that. Okay. That's fine. I think we can do another u substitution here. Any suggestions as to what the u substitution should be?
The x to the 8th power.
Nice. Right there. Because the derivative of x to the 8th is going to involve an x to the 7th. And that's just a big hint that, hey, you might want to look at that as a possible u substitution. Thank you. So u equals x to the 8th. That means du equals 8x to the 7th dx. Now in the integrand, I'll get x to the 7th dx. So I want to get that part by itself. I can multiply both sides by 1/8. But I'm going to do something else here, and that is I'm going to change my limits of integration. U of 1 is still going to be 1. U of b is going to be b to the 8th power. You don't have to change your limits of integration, but if you're not going to change them at this point, then the variables 1 and b really shouldn't be written as part of your integral, because your limits of 1 and b apply to x, not to u. All right, so let's rewrite this then. That's going to be the limit as b approaches infinity of the integral from 1 to b to the 8th of, let's see, it's going to be 1/8 du over x to the u. Are we okay with our substitution here? I'm going to take the 1/8 all the way out in front, move that up as e to the negative u. 1/8 limit as b approaches infinity of the integral from 1 to b to the 8th e to the negative u du. What's the antiderivative here? That'd be negative e to the negative u. That negative can come out in front. So negative 1/8, because it's a constant, it's not dependent on the b. Limit as b approaches infinity of e to the negative b to the 8th minus minus e to the negative first. This can be negative 1/8 of, this term's going to go to 0. Let me help motivate that by rewriting it a little bit as 1 over e to the b to the 8th minus 1, minus 1 over e. Might as well do it that way. This term, as b approaches infinity, goes to 0. So I'll have negative 1/8 times negative 1 over e is going to be a positive 1 over 8e. Boy, yes, go ahead.
I always get confused when it's turns into 0 and when it's infinity. Why would that be 0?
Because e to the b to the 8th, this number is going to get really, really large, really, really fast. And you're going to divide 1 by an ever-increasing large number. So think of it as 1 divided by infinity. That's going to go to 0.
Okay,
Does that help?
kind of.
E to the b to the 8th, well, I mean, even just an exponential function, e to the x is going to grow really, really quickly. And when you're dividing something fixed by an ever-increasing denominator, I mean, think about it, you know, if this was just 1 over n, really, you know, 1 over n, n's all your friends, you've got one piece of pizza, you know, you start dividing by more and more friends, pretty soon everyone's going to get nothing. So as n approaches infinity, you're dividing that 1 into smaller and smaller pieces because you have a huge denominator.
Okay.
All right. That's not quite where we finished, though. That's less than infinity. It's finite. Therefore, what? What can we conclude on that? Well, remember way back up here, this started out as a summation problem. We wanted to see if this converged. Because this is finite, therefore, and I'm being a little bit mathematically lazy here, 3 dots, therefore, this series, n to the 7th, e to the negative n to the 8th, converges by the integral test. Hey. Okay. How are we looking on that one? Let's do a couple more examples with the integral test, and I'm going to speed it up a little bit. Then we'll take a break and come back and finish with the p-test. P-test is actually going to be pretty nice. I think you'll like the p-test. All right, and it's not the p-test that you might be thinking of in terms of your probation officer. Different p-test. Let's see, that was example B. Let's take a look at example C. So the summation from n equals 1 to infinity of 3 square roots of n divided by 1 plus 3n to the 3/2. Wow. Well, let's think about our checklist here a little bit. This is continuous because on the range of values from 1 to infinity, this isn't going to be 0. You're not going to have a 0 or something negative underneath the denominator. Actually, it's the negative that would be a problem. So it's continuous. We got that going for ourselves. It's decreasing because as n increases, this number is going to be smaller than this one. This is going to get bigger faster than n to the 1/2 that you have in there. There's one more thing that we got to check. Oops, I wrote decreasing. That's the part that I was going to check. Continuous, it's positive. That's what I meant to check. Decreasing, yeah, it is decreasing, Well, you can see that by looking at the derivative. F prime of x. I'm going to help things out a little bit here. I'm just going to give it to you. It's going to be 3 minus x to the 3/2 over 2 square roots of x divided by 1 plus 3x to the 1/2 quantity squared. Wow, what's going to be going on with this? Well, we want to look at it on the interval from, say, 1 to infinity. Now in that range, this is going to be positive. Something squared is going to be positive, so the denominator is always going to be positive. But let's start with x equal 1. What can you tell me is going to go on in the numerator? If x equals 1, what's going to happen with 3 minus 18 times 1 to the 3/2?
It's going to be negative 15.
Yeah, it's going to be negative 15. And in fact, it's going to be negative for all values of x greater than 1, right? Because as this gets bigger, this is going to remain negative. So if it's negative on the interval from 1 to infinity, that's what we need. We need to know that it's decreasing. All right. So if it's decreasing, we can apply the integral test. And I don't think I'm going to go into as much detail with this one as I did with the last one. But let's take a look at the limit as b approaches infinity of the integral from 1 to b. So I'm just sidestepping a little step over, or of this 3 square roots of x plus 3x to the 3/2 dx. Now this one's another u substitution problem. Can anyone see what the u substitution should be in this case?
Square root of x.
If it was the square root of x, then the derivative would be, I have an x to the negative 1/2 power. There's no x to the negative 1/2 power down in the denominator. So it's a good thought, but that one doesn't get it done for us.
X to the 3/2.
Close.
3x to 3/2.
Closer.
Or just the whole bottom.
There you go. Yeah, close, closer, closest. And unfortunately, I don't have to go any higher than that. My voice has limits. So we're going to let this be our u. And then, of course, du is going to have 3/2 times 3, x to the 1/2 is going to equal our du. Let's see, and let's put the dx. Or 9/2 x to the 1/2 dx equals du. Okay. Let's change our limits. And I guess I'm going to give you more detail than I anticipated. U of 1 is going to be 4. U of b is going to be 1 plus 3b to the 3/2. If you look at what we have in the integrand, we've got the square root of x dx, or x to the 1/2 dx. So let me solve for that part. I could keep a 3 here, but I'm not going to be that motivated. Square root of x dx is going to be 2/9 du. Okay. When we make our u substitution, then we'll end up with the limit as b approaches infinity of the integral from 4 to 1 plus 3b to the 3/2 x dx is going to get replaced by 2/9 du. And the 2/9 times 3 is going to give me 2/3. Is that right? 2/9 times 3, yeah, it's going to be 2/3. Times 1 over u du. Yeah, that looks good. So this becomes the limit as b approaches infinity of 2/3 ln of u between 4 and 1 plus 3b to the 3/2. When you plug in that upper limit and take the limit, you're going to get infinity. This is not going to go to 0. And if it doesn't go to 0, or if it doesn't converge to something finite, I should say, not necessarily to 0, then therefore the sum diverges by the integral test. And I left out a few steps here, but the steps you can easily finish up. This would have to be finite in order for you to get a convergent series. Okay, we'll stop here. Any wrap up on example C before I kick it over and talk about p-test in the next hour? All right.
Yeah, I have a question.
Yeah, please.
Toward the top of the problem, like the first thing we do, I don't understand what the point of like positive, continuous, decreasing. I get that it has to be continuous, and I'm not sure what the other requirements mean if you can have it either positive or negative.
Great question. In order to apply the integral test, and I tried to highlight it here, your function has to be three things. It has to be continuous, it has to be positive, and it has to be a decreasing function on the interval 1 to infinity. So those are all three properties that have to be present with your function f of n. All three of these. Otherwise, you just can't do the integral test. Or if you did it, the results wouldn't mean anything. You have to have these conditions present in order to apply the integral test. So, great question. Appreciate that. Thank you. Anything else? Yeah, definitely glad that you gave me the chance to be a little bit more clear on that.
Can you leave that up for a second, or are we about to go on break? Or
Yeah, but I'll leave it up here.
Thank you.